So thanks again, Mara, for the introduction. So in this talk, I'll present some of the work me and my colleagues did at Laboratoire Kastler, Brossel, specifically on multimode quantum optics. So I'm aware that in the audience, you might not all be familiar with quantum optics, so I'll try to make this talk a bit pedagogical, and I'll introduce first the tools that are necessary to understand a bit this work. So that's continuous variables, modes, quadrature, and the notion of squeezing. Then I'll present the central tool in our experimental setup, which is a synchronously pumped parametric oscillator that we use to generate a particular quantum state. And then I'll present one type of work that we did with this quantum state. So what is quantum optics exactly? Well, it's quite a broad subject, but I would summarize it by saying it's just the study of quantum properties of lights and the associated application. So when you hear about quantum optics, it usually evolves around the typical quantum states of light that you can use. And those can be single photons, entangled states, which are very important in quantum optics. And squeezed light is closely related to entanglement. So you probably all heard about entanglement, but broadly speaking, it's a state of light that can show some non-local properties and show correlation that can't be accounted for classically, broadly speaking. And it's a very important resource for the application of quantum information. And so the range of application goes from metrology to quantum information, which encapsulate the computing and also communication and cryptography. So let me first talk about continuous variables. So there's two main ways to do quantum information, basically. There's the discrete variable setup, and then there's the continuous variables. And the difference is in the way you encode information in these two paradigms. So in the discrete variable, you work with photons, single photons. And so you encode variable into a discrete set of numbers. For a typical example is if you have two polarization states for your photon, then you can produce a state of light that's either horizontally or vertically polarized, or any combination of the two. And so you can encode your information into the coefficient of this combination. Now, a continuous variable is a bit different because you now encode information not into a discrete set of numbers like alpha and beta, but a continuous set. And so the information you encode in what we call the quadratures. So I'll explain a bit later what exactly quadrature is, but that's the main difference. And so the resources are different. In discrete variable, you mainly use single photons, and in continuous variable, basic resources, Gaussian states. Now, there's both advantages and disadvantages to these two methods. With continuous variables, the advantage is that it's more adapted to the current infrastructure for transmitting light, let's say. And also the generation of the entanglement resource, which is important, is done quite easily, and it's deterministic, as opposed to the discrete variable set where it's non-deterministic. But on the other hand, you don't have quantum speedup when you only use continuous variable states. So you need some discrete variable states or discrete variable type measurement to get some quantum speedup if you implement algorithm with them. So that's kind of a basic overview of DV versus CV. So now I'll go into what are the quadratures exactly. First, to make sure you're familiar with modes, I guess this you know. So broadly speaking, a mode is just a way for light to propagate. So it can be, for example, mode, longitudinal modes inside a cavity, or transverse mode of a paraxial beam, something like that. So basically, it's just a set of solution to Maxwell's equation in a given situation. Now, the mode is important to understand how we describe the electromagnetic field. So classically, you can just describe the electric field as a sum of all the modes. And then for each of the mode, you have two variables that describe your electric field. And that's what we call the quadrature. So in the case of monochromatic frequencies like this, you have two variables that describe this mode of frequency omega k. It's just Q and P, and they can be seen as a real and imaginary part of the complex field. Now, in the quantum description, those variables don't have definite values. They can take several values, and so they are promoted to operators. And the main consequence of this is that there is intrinsic variation in the measurement of those observable, and that results in some intrinsic noise in the electric field, if you wish. Now, so there's a typical spread in the electric complex vector, if you wish, and now these the uncertainties on the variables must respect an Heisenberg inequality like this. So it's very similar to momentum and position of a particle. So that's for the quadratures. Now, even for a state of light where there's no, well, for vacuum, where there's no photon, there is some uncertainty in these quadratures, and that means there's some intrinsic noise in the electric field. And that brings me to what a squeeze state is. So a squeeze state is the state of light in which one of the quadrature variants is squeezed below the noise, the limit noise that you get in vacuum, that we call the shot noise. And so to respect Heisenberg inequality, you need the other quadrature to have more noise. So we say it's anti-squeezed. And if you want to look at this state in a photon number basis, it's a superposition of even numbers of photons. So 0 photon plus 2 photon plus 4, etc. And so these states are very interesting because of this low noise property, you can use them for metrology, for example. So one of the famous example of use of these states is, and very successful one, is the use for gravitational wave detection. So in this example here on the right picture, you have the LIGO experiment scheme. So it's just a big interferometer, a big Michelson interferometer, and when the lengths of the two arms of the interferometer are equal, then the beams interfere destructively on the output. But when a gravitational wave distorts space-time, I will change the relative length of the two arms, and so some light will leak out, and you can measure that. Now, even when you don't have light on the output, you actually have some measurement noise, and this measurement noise comes partly from the shot noise that I just talked about before. So one of the use of squeeze light is just to reduce this shot noise. And so you inject into this output port here, to this dark port, you inject a squeeze state of light in order to reduce this noise that you get in your measurement. And that allows you to increase the precision of your measurement. And so that's been done in LIGO recently. Now there's some other application of squeeze states, and I'll come to that. In particular, it's very linked to entanglement, so it's used in quantum information. So the links between squeeze state and entanglement can be seen as this. So if you have two squeeze states, one is squeezed along Q quadrature, let's say, and the other one along P, and now interfere those states onto beam splitter. Just like in the classical case, on one output of the beam splitter, you have the sum of the electric field of the input, and on the other output, you have the difference. And so if you look at the statistic of the quadrature, if you look at the output individually, you actually get something that's circular like this with increased noise. So in here, the central dotted line represents the noise that you would get in vacuum state. So here you have more noise. So when you look at the two outputs separately, they just look like noisy states. But when you look at them conjointly, there is some correlation between the quadrature that you get on one side and on the other side. Particularly, the Q quadratures are correlated and the P quadratures are anti-correlated. And this type of correlation goes beyond what can be explained classically. So this is what we call an EPR state. And so it's a continuous variable version of entangled state. Now, the way to produce squeezing and then EPR state is to use, one way to produce them is to use a nonlinear crystal. And that's what we do in our experiment. So the idea is just, if you have a certain frequency pumping your nonlinear crystal, there is some probability that one photon can convert into 2 photons of lower frequencies, and you just have to respect the energy conservation and momentum conservation as well. And because they're produced by pair, the state you get is a sum of even number of photons, and this is just a squeeze state. So usually we put that into a cavity, and that's what we call an optical parametric oscillator. And the cavity here just enhances the nonlinear effect, and so it allows you to produce squeeze state with even more reduced variance of one of the quadratures. All right, so now I'll come to our experiment. Our experiment, the central resource is an OPO, but it's pumped by a femtosecond laser. And so this laser, if you look at it so it produces a set of pulses very short. And if you look at that in the spectral domain, it's what we call a frequency comb, because it contains many frequencies, like many individual frequencies with a given envelope. And in our cases, there are like 100,000 of frequencies inside the envelope. So it's a very broadband laser. And so when we pump a nonlinear crystal with that, each of these frequencies can convert into signal and idler photon. And this means that we get signal and idler photons in many different frequencies coming from many pump different photons. And so there's a complex correlation between all those frequencies that emerges from this pumping. But you can sort of diagonalize this problem in a way. And so what you get on the output of a synchronously pumped parametric oscillator is actually a set of squeezed mode. And each of the mode has a spectral shape that is like this. So it's a frequency comb with a given envelope. And so the first mode that has an envelope very much like the pump we use. The second mode has an envelope with a pi phase shift like this, etc. And so there's more and more modes, and the squeezing decreases as you span a higher order mode. So the output of this popo is just like if you had many different squeezers in parallel, except each of the squeezed mode has a different spectral shape. All right. So that's another picture that shows popo. One last thing is to look at how we measure those states once they're produced. And for that, we use homodyne detection. So homodyne detection is just interfering the beam of interest, that's the dotted line here, with a very bright beam. And then you you measure both, you interface on the beam splitter that's balanced, and you measure both outputs. And the subtracted photocurrent that you get can be shown to be proportional to the quadrature of the input beam. And the quadrature that you measure is in the mode that your local oscillator is in. So in that case, our input is just a superposition of many different modes, each squeezed. And you can select which mode you measure by changing the local oscillator spectral shape. So if I put the spectral shape of the first mode, then I measure the squeezing of the first mode. And then I can measure the difference mode like that. And the way we select, or the way we tune our local oscillator to match the different modes is with a pulse shaper. So pulse shaper is a standard technique for shaping the spectral amplitude of a beam. We just send our pulse into a grating that decomposes different spectral components, and we image them on a SLM. So SLM is just an array of liquid crystal that will change the phase of the different frequency components, and then we recombine them, and that allows to shape the amplitude and phase of the spectrum of the light. All right, so this is an overview of our setup. So we have this laser, we pump an OPO with it, and we also shape a local oscillator in order to measure this multimode squeezed vacuum that we create. All right, so now I can explain what we do with those states actually. So one of the applications that I'll present today is cluster state. But first I need to give a bit of context. So when doing quantum computing or quantum information processing, the sort of original scheme is circuit quantum computing, where you have an input quantum state, and then you apply some gates to it. And so these gates that are represented with blocks can be applied on several inputs, and they do some operation, and then you measure the output. And this is what realizes your algorithm. Now, one of the difficulties is when you have operation that acts on several inputs like this. So gates that are applied on many modes are difficult to produce. But there's another way to do quantum computing, and that's called the one-way quantum computing. Instead of having input state and having some gate applied to it, you produce a large state with nodes like this. And each of these nodes is correlated to all the other nodes. And instead of applying gates to it, you will just do single mode measurements. So in this example, you do a measurement on the first column, and on each of the nodes, you measure something different. And then depending on the result of this measurement, you can measure the second column. And by doing so, because all of the lines and columns are correlated, you can show that this, you can realize any algorithm that you can do with circuits in this way. So it's a sort of different way of doing computing, where instead of having the difficulty of producing gates that apply on different states, the difficulty is just to produce the initial state, and then you only do measurement on single modes. And so that brings me to the interest of our setup in this context, is that the when I explain the link between entanglement and squeezing, I present this interfering to squeeze state to get this EPR. Well, if I look at it in terms of the cluster state I just talked about, before you interfere them, is just two modes that are independent that I can represent with those circles like this. After you interfere them, they are entangled. So I can represent them with nodes with link like this. And this is a very simple example of what I call a cluster state. It's just two nodes that are correlated. Now, in our setup, we produce many squeeze states in different spectral modes. So we can produce cluster states that have more nodes and a bit more complicated. And so then you can imagine producing many types of clusters like this. So now I'm going to present some work that we did recently. So I first mentioned at the beginning of this talk that when you use Gaussian state, so CV, the basic CV state, you don't have any quantum speedup, so you need some discrete variable ingredient. And that's the recent work we did, is introducing this discrete variable ingredient into those cluster states. In particular, what we did is subtract single photons from the nodes of these cluster states. By subtracting single photons out of these nodes, you can produce a state that has this ingredient that you need for doing quantum information. So the way we subtract a photon out of this complex state is by using another nonlinear crystal. So we have our input, which we want to subtract a photon from, and you just send it into the crystal along with another beam that we can also shape into a given spectral mode. And the spectral mode are orthogonal, so they will only interact with the corresponding spectral mode of the input. And they can generate some frequency generation, which generate a photon at higher frequency that we can then detect with a single photon detector. So when we detect a photon in the blue here, we know that one photon has been removed from the input. And we also know that this photon has been removed from whatever shape we put on the gate beam. So this way we can select which node we subtract from. So this is another overview of this setup. And so what we did is try and subtract from different nodes, either the squeeze mode or superposition of the squeeze mode, which represent correlated nodes in the graph I presented before. And then we measure the nodes of this graph to see the effect on the state that we generate. So this is an example. If you don't subtract and you measure, say, the first mode that I call HG0 there, at first you just have a squeezed vacuum state. So when you measure the quadrature, one quadrature has a large noise, the other on the orthogonal quadrature, the noise is reduced, that's just a squeeze state. And now when you subtract a photon, you see that the quadrature distribution changes. And that shows a characteristic of the subtraction. So this type of state, when you subtract, is called a Schrödinger's kitten state. And an interesting feature of these states is that its Wigner function, which represents the quadrature, the phase space distribution, if you wish, can take some negative values. So when you see negative values in the Wigner distribution, it means that this state has potential for quantum information processing. It has the quantum speed up advantage, if you want. So our next step was to try and subtract from the different modes and verify that this subtraction was mode selective. So this table shows the input modes that we have and which mode we decide to subtract in by shaping our gate beam. And so what you can see here is that the mode we don't subtract in are unchanged. So when we subtract in HG1, for example, mode HG0 is unchanged, but HG1 has this Wigner function change. And finally, the last step was to look at the effect of subtraction in graph states. So we looked at different configuration of graph states. So a linear graph state, for example, and we looked at the question, what happens when you try and subtract a photon from one node? What happens to the other nodes? And so we basically investigated those graph states and the effect of subtraction. And so what's interesting is that because you have correlation between those nodes, you can subtract a photon in one node and see the effect of this subtraction on the other nodes. That's the case, for example, on this upper right corner of the linear cluster here. When we subtract in the last node, we actually see the stronger effect is in the third node here. And so along with that, in our team, we did some theoretical research on the condition for producing what we're interested in, which is the Wigner function negativity in other nodes when you subtract in nodes that are neighbors or next to them. All right. So that's the end of my talk. I'd like to thank the organizers again, Paul and Marin, for letting me do this talk, and also all the other people at MEMO. I know this may seem a bit abstract, so please hit me up with any questions. And thank you.
Okay, thank you. We have a question from Elena. So if you have any questions, you can ask them in the Q&A box. And there's a question from Elena. Could you comment more on the quizzed states for communication? Does it allow to encode more information into the beam?
Yeah, I'll comment about that. So let me just scroll back to. Okay, so there's different things you can do with squeeze states. So one, when you use them for communication, usually, okay, so there's one standard thing in communication is quantum key distribution. And the idea behind quantum key distribution is just to allow two separate parties to share a key that is known only to them and is secret. And one way to do that, which is, I should mention, it's not the preferred way because it's somehow a complex way to do it, but is to have these two parties share one mode of an entangled state. So in the particular case of the EPR state I just talked about, if you have those two quiz states, you interfere them, and then you send one arm of the EPR to Alice, say, and the other arm to Bob, and then they do measurement on them. Those measurement results will be correlated in a way that allows them to share a secret. So it doesn't necessarily mean you can encode more information. In that case, it's just about sharing a secret. Now about the second, I don't know if that answers your question really, but it's in terms of so that's for QKD, but in terms of if you're trying to use those states not to transmit or crypt information, but to do calculation like algorithm, it's always a bit complicated, the idea of having more information encoded, because let me go back a few slides. When I talked about at first about DV and CV here, I say you can encode information, for example, in DV, in those alpha and beta coefficients that represent how your photon is a superposition of horizontal vertical polarization. These alpha and beta, they're just complex number. So potentially you could store infinite information in them. So so it's very different from classical bits, in which like you just have 2 units of information as are 0 or 1. Here, alpha and beta are complex numbers. So in theory, you could put infinite information in them. But the thing is, in quantum information, when you measure something, it's usually a statistic measurement. Even if the state is deterministic, you always get there's several values that an observable can take. So this means that in practice, you cannot encode infinite information, because you cannot do a measurement without noise that would allow you to recover alpha and beta perfectly for any state. So yeah, so in terms of using the states for processing information, even if it seems that you can encode more information, it's the full story is more complicated than that. Right, that's a long answer, sorry. The second part of the question is like the problem connected to transferring information. So there's something very important in those type of states that are superposition is that they have a degree of coherence in this superposition. And that's something that you lose whenever you transmit them in a noisy channel. So in general, quantum states are more sensitive to noise than classical ones. So that's one of the main problems of quantum information is noise. Well, the states are quite sensitive to noise in general.
Okay. I don't know if there are some other questions.
I may have one.
Yes.
Yeah.
Sorry,
Go
it's
ahead.
not actually my field, but so like I would like to have like more intuition about this. Like, how do you know that your process or your system is good in generating squeezing states? Like, I know what you're measuring are the quadratures, like here it says. So how do you know, like for example, that like this OPO, this down conversion will generate squeeze state? And are there other examples? Can we have some intuition, like for people that were not exactly in the field?
Yeah, sure. So, well, how you know it is you actually measure the state, and this allows you to know. Yeah. So I presented the way we measure the state. What was it? Here with homodyne detection. So here in this case, let's say you don't have these complex modes. You just have a single mode OPO. When you have your OPO on this side, you're trying to measure the state that comes out. If you don't send your pump beam to your OPO, what you measure is just vacuum. And so what you will measure from this homodyne detection is just the noise, the typical noise I talked about that comes from the fact that the quadratures don't have definite value. Now, you do see that you have a squeeze state because you put your pump in your OPO, and you see the noise in your oscilloscope that just reduced below that. So it's kind of funny to see that by unblocking the beam, you actually reduce the noise that you see. But yeah, the idea is just you measure those quadratures, and that tells you if you see that the quadrature is below vacuum, then you know you have squeezing. And vacuum is easy to measure. You just block whatever beam you have here, or you stop pumping your OPO, and what noise you'll see is just the noise from vacuum. Now, yeah, does that answer your question?
Yeah. But I was also wondering, like, what other type of phenomena can produce this squeeze state? Like, not only down conversion, for example.
There's many different phenomena that can produce. Well, I'd say, as far as I know, it always involves some nonlinear crystal or some nonlinearity in a medium, because whenever you have some nonlinearity, you can have some photon conversion like this. So if you have second order nonlinearity in the quantum distribution, that's whenever you have nonlinearity like this, you have a possibility for pump photon to be converted into a pair of photon. Now, when you do it in a continuous variable to produce squeeze state like this, you send a pump that contain many photons. And so on the output, you get a state that also contains many photons. And in the particular case I presented, it's just like a superposition of pairs. Another way people also produce not squeeze state but entanglement in a discrete variable is also use this nonlinear crystal, but they pump them very weakly so that they only send a couple of pump photons. And so then what you get is not a superposition of many photons on the output, it's just single pairs of photons. But yeah, in general, to answer your question, it's just non-linearities like this can produce photon conversion, so you can produce squeeze state with that.